Okay, so the last week we've been looking at the force on a wire in a magnetic field that carries a current. So if you place a current carrying wire in a magnetic field, you'll actually get a force on it. So in this case here we've got a magnetic field of 2 × 10⁻³ Teslas into the board. You can tell it's going into the board because it's the back of an arrow. So the back of an arrow, if you imagine the feathers there of the arrow, it's in a cross shape. That means the arrow is going away from you. So if you're seeing a cross, the arrow is going into the board and you're looking at the back of the arrow. If you see a dot though, you're seeing the point of the arrow, it's coming towards you. So dots would represent a magnetic field coming towards you. So what we've got here is a magnetic field going in, you've got a current going down, okay, 0.5 amps, and therefore you get a force on it. So the size of the force, don't forget, is F equals BIL sine theta, and you might sometimes see it written as ILB sine theta as well. But it's the magnetic field, the current and the length. So that's what we've been working with. And don't forget the right-hand rule. So with the right-hand rule, the current is always the thumb, okay, and the field is shown by the fingers. Now if you just had a wire with a current through it like that, it's true that there's a field going around the wire like that, the way the fingers are going in circular field lines. But in this case here, it's sitting inside another field, and that field is going into the board. So you stretch your fingers out to override that. It's going into the board. The force will be shown by the palm, in this case 90 degrees to the right. Okay? So what we want to look at now is an application of that involving speakers. So speakers come in all different sizes. You have tiny ones up to big ones, and they all do different sort of jobs, but they respond very similarly in the way they actually work. So we've got some speaker diagrams here. If you look at one of these in cross-section and cut through here, what you'll find is some key parts you need to know for the course. So here for part A, you've got a permanent magnet. And I'll show you a little clip of this in a minute, which will show you the magnet picking up nails and stuff. So that's a permanent magnet. So let's say you've got a north part there, a north pole. This wraps around and becomes south on the outside there. And don't forget we've cut through. There is a groove in that magnet where you put a voice coil. So this is your voice coil here, which may consist of many turns of wire, okay, circular turns of wire. And that's being fed by a pair of wires coming in where your current is coming in as alternating. All right. Now attached to this voice coil you'll find there's a paper cone or diaphragm, so that's part C. Sometimes it's made of cardboard or plastic in some cases, and that's going to vibrate with the coil when the coil moves. So that's it inside view. Okay. Here it is in front view, just looking at this part here. So you've got a north pole in the centre, south pole surrounding it, and you've got a groove there, excuse me, with a coil of wire inside it, okay. So let's imagine that the coil of wire to start with has got a current going through here that is clockwise. It's actually sitting in a magnetic force field which is radial and going out. And don't forget magnetic force fields or fields go from north to south, because you imagine it's a north test pole, and a north test pole will be forced away from the north to the south. So we've got a radial field here coming from the centre that goes outwards north to south. So what will that do to the wire that's in there, the coil that's in there? Well, if you check your right hand rule there, if we look at this position here, we've got a current going down with a thumb. Thumb is always current. The field it's sitting in now is that way, from north to south, the red line there. And so that will be forced out. Now if you check this side here, the current on this side is coming up, and the field is going to our left, which means forced that way, out towards us as well. So if you check it, no matter which position you've got this in, the coil always experiences a force out of the board, and so it'll be forced outwards. Okay? Now just also bear in mind here that you've got a constant large force, so the force is maximum, and the reason for that is that the angle that it always makes to the field is theta is equal to 90. These degrees here, if the current's going down here, like that, and the field is going sideways, you've got a 90-degree angle. According to your formula, you're going to get a maximum force based on that. And that will occur all the way around here on the coil. So it's not only a maximum though, it'll also be constant on all parts. You get an equal size force on all sections there, and that's why you want this radial field to provide that sort of constant force there, okay, because of the shape of it. So it's forced outwards in the first instance. Now, what would happen if we turn the current around and went the other way? Because that's what's going to happen next. In the first instance, we've got a magnetic force and it's forcing it outwards. If you reverse the current, the direction of the magnetic force will reverse and it will go in, because the current is now going up at this point. Field is that way, it's going to be pushed into the board, and again that's going to happen all the way around. So you get a magnetic force pushing it out one way, current reverses, magnetic force pushes it in, and if it's alternating, of course, it's going to do that continuously, because what you've got for alternating current is this sort of a behaviour. Current versus time, it goes in one direction and reverses, another direction and reverses, and so that's going to cause this to go in and out. So let's say you had a current that was 50 hertz that was coming in here, all right, electrical current through there. That would cause this to reverse 50 times per second. So if the coil is reversing 50 times per second, or vibrating 50 times per second, 50 hertz, you will find the attached cone here will actually vibrate at the same rate, pushing the air particles in front and creating a sound wave of 50 hertz. And naturally, if you increase the frequency of the current here to 100 hertz, you're going to get twice the frequency of vibration, and the pitch of this sound is going to go to 100 hertz and be higher when you listen to it. Okay? So that's the essential parts of how it works. If you look at it from a point of view of a picture, like this here, so what we've got here is the speaker there, and you can see the speaker is actually magnetic. Okay? Like that. That's your speaker, which is magnetic. Picks up the things. So that's the back of it. If you tear the diaphragm off here, and this person's cutting the thing off there, you'll find inside the magnet there with a groove, and inside that groove there should be a little paper cup, or paper cylinder, sorry, with the voice coil around it, which might be many turns. That's the part that vibrates and is attached to here. You can see the wires where they come in as well. So with your magnet there, then you've got a ring magnet there. Your voice coil goes inside it. You send the current through. Make sure there's a diaphragm attached or a cone attached to that coil, and you'll find it vibrates. When the current's in one direction, it pushes out. When the current's in the other direction, it pushes in, or pulls in rather. Okay? And that vibration you can see here in this diagram there. But that's what's producing your sound wave through the air. Okay? You can actually make one out of a simple coil and a plastic cup and a magnet as well. So I'll show you one of those that's been done here. He's made a coil there by wrapping it around just a little tube, cylinder. You take that and you put it onto the bottom of a plastic cup with a magnet in the middle of it. I'll take the ends off, by the way. So he's just got that at the bottom of the cup. You put a magnet inside the cup, just inside there. That's in the bottom there. And all you need to do now to get this to be a speaker is just feed in an alternating current, which is what he's going to do in a second there. Okay, so that's the speaker there. So the speaker that they're using here will be very good quality here. The paper cup one, or plastic cup one, will sound like this. So that's just feeding into a plastic cup with a coil. So key parts for the exam then. If you're looking at this and they ask you how does a speaker work, or explain how a magnetic voice coil speaker works, the main point to point out is there's a magnetic force out of the page when the current's in one direction. Okay? When the current is reversed, that magnetic force is going to be in the opposite direction. Okay? That's causing the AC signal to make the coil vibrate, because it's going to go backwards and forwards. And if it's vibrating, it's going to move that diaphragm and move the air particles and produce sound. So you're kind of looking at magnetic force in one direction. That reverses when the current reverses. Obviously an AC signal will cause it to vibrate then, and you're going to move your air particles through the diaphragm. So if you're looking at 4 marks, those 4 points should cover things pretty well. So if you look at the side view version of that, you've got here, cross section this way, you've got the current coming out of the page here because it's actually the dots. So the current's coming out because the arrow is coming towards you. And if the current's coming out and it was in a magnetic field that goes from north to south, it's going to be forced to the left. So current's coming out, your field is up from north to south, it's going to force it to the left. If you check this other one, the current is going into the board, it's the back of the arrow, the cross, so it's going in, that one there. So current goes in, the field is going north to south down in the bottom half, so it's going to be pulled across this way. Okay, in, down. So both of those are forcing it to the left, and in fact all points of that coil will force to the left and will be pulled inwards. Okay, when the current reverses, obviously it goes in the opposite direction. Okay, and that causes the vibration. So when you're looking at the speaker then, you should be conscious of the parts of the speaker and the explanation as to why the alternating current causes the force to go outwards and inwards, making it vibrate, making the particles vibrate via the paper cone or the diaphragm.